Alright, today we're moving into randomized complete block designs. In practice, we almost never get perfectly homogeneous conditions when running experiments. There's always something, day effects, batches, operators, that introduces variability. Blocking is one of the main tools we use to deal with that. It allows us to remove known sources of variation so that we can make cleaner comparisons between treatments. And importantly, it can also help us generalize results beyond just one specific set of conditions. There are really two reasons we use blocking. First, sometimes we have no choice. If we ignore something like day-to-day variation, it can completely distort our results. Second, sometimes we block to strengthen our conclusions. If we show treatment effects hold across different types of experimental units, then our results are more broadly applicable. So here we're categorizing nuisance factors. If they're controllable and known, we block. If they're unknown, we rely on randomization. If they're uncontrollable but known, we might use something like analysis of covariance. This table is really just a decision guide for how to handle unwanted variation. The key idea here is simple. We want to compare treatments within groups that are as similar as possible. By doing that, we remove variability due to the blocks, which makes our treatment comparisons more precise. Now, blocking comes at a cost. We lose full randomization. Instead, we randomize within each block. So for example, if we run an experiment over 2 days, we finish all runs for day 1 before moving to day 2. But within each day, we still randomize. This is a subtle but important point. We don't test blocks for significance. They're not randomized, and they're not of primary interest. They're just there to reduce noise. A randomized complete block design means every treatment appears in every block. That's what makes it complete. So each block gives us a full comparison across all treatments. Let's go through an example. We're comparing 4 tips on hardness measurements. The coupons introduce variability, that's our nuisance factor. So instead of assigning tips randomly across coupons, we apply all 4 tips to each coupon. Now each coupon becomes a block. This gives us a two-way structure, treatments and blocks. And our goal is to compare treatments while removing the variability from coupons. The model includes 4 components: overall mean, treatment effect, block effect, and random error. We're explicitly accounting for block-to-block differences. Same assumptions as usual: normality, independence, constant variance. Nothing new here. We're still testing whether treatment means are equal. You can write this in terms of means or effects, it's the same test. We check residuals like always, but now we also look at residuals versus blocks to make sure nothing systematic is left. We partition variability into treatments, blocks, and error. The F-test is still based on treatment mean square divided by error mean square. Blocks help reduce the error term, that's the whole point. Error is what remains after accounting for both treatments and blocks. Because of blocking, this error should be smaller than in a completely randomized design. Here's the full ANOVA table. Notice we now have a separate component for blocks. But again, we don't test blocks, we just use them to improve precision. This is where you evaluate whether blocking actually helped. If the block mean square is large relative to error, blocking reduced variability, good. If not, you may have actually hurt power. If blocks are random, interpretation changes. We're now generalizing treatment comparisons across a population of blocks. Here we're comparing washing solutions with days as blocks. The key idea is that days introduce variability, so we block on them. Here's the data laid out by solution and day. Each column is a block, and each row is a treatment. Looking at the ANOVA results, both solutions and days are significant. So blocking was absolutely necessary here. Now the natural question is, what if we have more than one nuisance factor? In this example, we have 2 nuisance factors, operator and batch. So we need a design that can handle both. This leads us to row-column designs, where we block in 2 directions simultaneously. The design is structured like a grid. Rows represent one blocking factor, columns represent another, and treatments are assigned within cells. Once we define the structure, we randomly assign treatments to the cells. That preserves randomization within the constraints of the design. A Latin square is a specific case where each treatment appears exactly once in every row and every column. Here are examples of Latin squares. Notice how each treatment appears exactly once per row and column. We usually start with a standard Latin square and then randomize the labels. This gives us flexibility while preserving structure. If one blocking factor has fewer levels than treatments, we use a Uden design. It's a constrained version of a Latin square. Here's an example of a Uden design. Notice that we no longer have a full square, but we still balance treatments across blocks. We can replicate these designs to increase precision. For example, stacking multiple Latin squares. This shows how replication works in practice with multiple squares. The model now includes row effects, column effects, treatment effects, and error, still additive. We partition total variation into rows, columns, treatments, and error. Same logic as before, just extended. We check assumptions and then proceed with inference on treatments as usual. Now we analyze the rocket propellant data. The key question is whether propellant types differ. The ANOVA shows that treatment type is significant. From pairwise comparisons, we identify which treatments differ from each other. The main differences are between BA, DB, and DC. Now another example, traffic light sequences with two blocking factors. Here's the data layout across intersections and time periods. The ANOVA shows that sequence is not significant, but time period is. So what do we do if we have more than two blocking variables? We use a Greco-Latin square, which allows us to control three nuisance factors simultaneously. Here's the structure, two Latin squares superimposed. The model now includes three blocking factors along with treatments and error.